That there is the belt of Orion. The big red star is Betelgeuse. And if we zoom in about 3,100 light years, we come to this bluish-white blob of a star that looks like it could be wearing a beanie. Of course, it's not really wearing a beanie. What's actually going on is this is a binary star system. Two stars orbiting around each other. And they're both cranking out this bright whitish blue light, but they're so hot that they're actually more visible in the UV spectrum. In spite of their similar colors, these are actually very different stars. The heavier one, HD 45166A, is a B7V main sequence star, and it's up here on the Hertzsprung-Russell diagram. The other is designated HD 45166B. It's a Quasi Wolf-Rayet star, and it's the one that recently made headlines. In this study that was just published a few days ago, the researchers determined that it has all the ingredients necessary to become a magnetar, including a very powerful magnetic field. But as I'll explain, there are several obstacles it has to overcome on the way to achieving this dream, just like all of us have obstacles to our dreams. So today I'm going to talk about this binary system and both of these very interesting stars in it. I want to get into their dynamics and where they are in their life cycles. I also want to talk about magnetars and some of the things that are known and unknown about them. I also want to talk about the smaller star's magnetic field, how powerful it actually is, and how it was measured from Earth. Like, really, how did they even do that? And it also turns out this binary system has a pretty crazy origin story. So let's get into it. I'm Cameron and this is my channel. Welcome to the Sexy Universe. The HD 45166 binary system was first observed in 1922. It has an orbital period of about 8,900 days, which is close to 24 years and 5 months. All orbits in space are at least a little bit elliptical, and some, like comets, can be very elliptical. This one isn't extremely eccentric. It actually looks more like an imperfect circle. The furthest separation of these stars in their orbit is 10.5 astronomical units, and the nearest they come to each other is 9.29 astronomical units. And for reference, the distance from the Sun to Saturn is about 9.5 astronomical units. So they orbit at about the distance of the Sun to Saturn. And there's no evidence of exoplanets in this system, and given how chaotic the gravity dynamics are, there's no reason to expect that there would be any planets with stable orbits. HD 45166A is the heavier star. It weighs about 3.4 solar masses. Its radius is about 2.6 times the radius of our Sun, which makes its volume about 18 times our Sun's volume. So if our Sun had the volume of this spray bottle, the star I'm talking about would have about as much volume as this bucket. So there's the comparison. The surface temperature of our Sun is around 10,000 degrees, but the surface of this star is much higher. It's at about 23,000 degrees Fahrenheit. And of course, things get much, much hotter in the core of stars, and they can measure anywhere in the millions to hundreds of millions of degrees. And with truly supermassive stars that are far into their shell burning phases, their core temperatures can get into the billions. These B-type stars have excellent convection currents. So during their hydrogen burning phase, they just don't accumulate a whole lot of helium in their core. That mixing allows them to keep fusing hydrogen at a phenomenal rate. They sustain very high temperatures and burn through their hydrogen very quickly during this phase of their life. Later in their life cycle, other types of fusion take place, and we'll talk about that in a little bit. The lighter star is HD 45166b, and it's the Quasi Wolf-Rayet star. The reason it's called a Quasi Wolf-Rayet star is because it's smaller and it has a different origin story from other Wolf-Rayet stars. Wolf-Rayet stars are basically stripped down stellar cores that have blown off almost all of their hydrogen and are now fusing helium and carbon. These stars originally had masses anywhere from 10 to 25 times what our Sun had. But once they're stripped down, their mass is only somewhere between 2 and 4 solar masses. In the Wolf-Rayet stage, they get incredibly hot surface temperatures, all the way up in the millions of degrees Fahrenheit. And that makes sense because the star's outermost layers have already been blown away. So these guys have passed the initial stage of their life. Every fusion reaction requires some energy input, and then there's some energy output. The best return on this energy investment is hydrogen fusion. And this is true even though there are several steps to it. And the reason there's several steps is because neutrons have to be created in order to make the protons stick together to form stable helium atoms. Helium, carbon, and other elements have much lower rates of energy production. But later in a star's life cycle, many more atoms are fusing all at once, so the overall energy output is much higher. The energy output of a Wolf-Rayet star produces incredibly high temperatures and powerful stellar winds. So the amazing nebulae that surround these guys is actually a result of the hydrogen in their outer layers being blown away by these powerful solar winds. The Wolf-Rayet phase lasts anywhere from millions to tens of millions of years. And you can compare this to the hydrogen burning phase of a very large star, which is on the order of hundreds of millions of years. As I mentioned, the Quasi Wolf-Rayet star in this system isn't a true Wolf-Rayet because it isn't heavy enough, and as a result, its surface temperatures aren't as high as a regular Wolf-Rayet star. This particular star weighs about 2 solar masses, and its radius is about 88% of that of our Sun's, which puts its volume at about 2/3 of our Sun's volume. And its surface temperature is only somewhere around 100,000 degrees Fahrenheit, which is still very hot, much hotter than the vast majority of stars. So in this system, we've got this Quasi Wolf-Rayet star, which is past its hydrogen burning phase, and we've got the B-type star, which is still in its hydrogen burning phase. The B-type star, when it starts burning helium and carbon in its core, it's not going to become a Wolf-Rayet star. Instead of its outer layers blowing completely away, they're simply going to expand greatly, probably until it's about 10 to 15 times as wide as our Sun. And at that point, it'll be called a blue giant. This blue giant phase, like a Wolf-Rayet phase, can be expected to last tens of millions of years. So the smaller star in this system is going to go through the in phases of life hundreds of millions of years before the B-type star gets to the final stages of its life cycle. What's made headlines for the smaller star is its incredibly powerful magnetic field, and this is an artist's rendition of it. Its magnetic field wouldn't actually look like this, though. At least it wouldn't look this well organized. The magnetic fields in stars, molecular clouds, and galactic filaments results from the movement of pockets or rivers of hot plasma. And since all that plasma would be roiling around in the convection currents of a star and popping out as sunspots over its surface, instead you get these spaghettified magnetic fields with magnetic eruptions coming off the surface as well. Magnetic field strength is usually measured in Teslas. And it's not technically a measure of field strength, it's a measure of field density, but it shows up as strength when we interact with it, so the terms are used interchangeably. The researchers initially knew this star had a pretty powerful magnetic field just by looking at the variability in the helium spectral lines. That variability also allowed them to determine the rotational period, which turned out to be 124 days. The spectrum also has this section, which is labeled OFP. This represents the carbon and nitrogen spectral lines. And the way these lines are kind of split apart is another indication of a strong magnetic field. But the way they got a measure of the actual magnetic field strength was by looking at the difference between these two charts, which represent the spectral lines of different ionization levels of oxygen atoms in the star. The difference between these lines was analyzed using the Zeeman equation. As you can imagine, this equation can get pretty complicated when it's working in multiple dimensions. But in this case, the researchers were able to use the simplified version. And what the equation says is that the measured wavelength is equal to the expected wavelength plus distortion by the magnetic field. The actual field strength is represented by the term B in this equation. And by taking the measured data and solving for B, they got a magnetic field strength of 4.3 Teslas. I'll explain what that means. The strength of the Earth's magnetic field is somewhere around 35 to 65 microteslas, which is about 1/100,000th of this star's. The average MRI machine runs between 0.5 and 1.5 Teslas, though some can go all the way up to 7 Teslas. So being on the surface of this star would put you in a magnetic field about 3 to 4 times as powerful as the average MRI machine. here's a little bit of a deeper explanation. A Tesla is defined as a magnetic field that produces a Newton of pull on an object with 1 coulomb of charge going through it at 1 meter per second. Magnetic and electrical forces are always perpendicular to each other. So if a charged object moves horizontally through a magnetic field, it's either going to be pulled upward or downward. And that's going to be determined by the direction of movement of the charged object. A Newton is the amount of force generated by the Earth's pull of gravity on an object that weighs 1/3 of a pound, like this apple. I actually weighed this apple at the grocery store and determined that it really is 1/3 of a pound. And you've probably heard the term Newton's apple, and that it was an apple that landed on Isaac Newton's head and gave him the inspiration to come up with his universal law of gravitation. And this is where the story comes from. The average apple has a pull of 1 Newton. So if you were on this star, moving 1 coulomb of charge over the surface at a rate of 1 meter per second, it would produce about 4.3 of these apples worth of pull on your hand. So the next question is, how would you get something that has a coulomb of charge? Well, as you can see, this here is a AA battery. And the average AA battery holds 9,000 coulombs of charge. So moving this battery at a rate of 1 meter per second across the surface of the star would produce a downward pull equivalent to 38,700 of these apples. Very quickly, if you're enjoying this video and feel like you're getting something out of it, now would be a good time to click the like button and leave any thoughts or information you'd like to share in the comments section below. I'm also hoping to get monetized someday, so if you'd like to support my work, the best way you can do that is by clicking the subscribe button. The mass of this star, at about 2 solar masses, is enough to exceed the Chandrasekhar limit. The Chandrasekhar limit is basically the highest mass a white dwarf star can have, because if the mass is above that, it produces too much pressure for the electrons to hold up. So if a star exceeds that limit, its endpoint is not going to be a white dwarf, it's going to be a neutron star. In one of my previous videos, I explained the Chandrasekhar limit and how it works. I'm going to put a link to the timestamp in that video where I explain it. So if you'd like to learn more, you can click on that link that I'm going to put in the description. But basically, because of how heavy this star is, if it were to collapse now, it would not become a white dwarf. Instead, all the electrons in the core of this star would be pushed down into the atomic nuclei and merge with the protons. When that happens, the proton and electron pairs are converted into neutrons, and they release a whole lot of energy and a whole lot of neutrinos when that happens. The outermost layers of the stars are blown away in a massive supernova. And what would be left over from all this is a nebula and a neutron star. Currently, this star's diameter is about 88% of our sun's diameter, but the diameter of a neutron star is somewhere between 12 and 20 miles. And when that collapse happens, the magnetic field collapses down as well, but it doesn't lose its strength. Instead, it's concentrated into that smaller space. And as a result, the magnetic field of 4.3 Teslas would go up to 1.11 times 10 to the 10th Teslas. And what that means is this AA battery that would produce 38,700 apples of downward pull on the surface of this star. On the surface of the equivalent neutron star, it would have the pull of 100 trillion apples. And that would mean we don't just have a regular neutron star, we have a magnetar. The magnetar is only thought to exist in the infancy phase of a neutron star, so it's just a temporary short part of its life. And of course, not all neutron stars come from stars that have powerful magnetic fields. So not all neutron stars have a magnetar phase. So the magnetic field would need to be preserved through the collapse and supernova, and there's every reason to believe it would be. And then the field continues to exist because of fluid dynamics going on the inside of this extremely hot neutron star. Like every other very large object, neutron stars have layers. And that includes an inner core, and nobody's exactly sure if that inner core is going to be made out of neutrons, or if the neutrons are going to be so hot and so compressed that the quarks actually dissociate. The outer core would consist of neutrons in a semi-liquid state because of all the heat. And then there would be a solid outer crust consisting entirely of neutrons as well. Outside that outer crust, the neutron star has an atmosphere. This atmosphere is incredibly hot and incredibly dense. and it's only a few centimeters thick. This atmosphere would consist almost entirely of hydrogen, helium, and carbon atoms. The Magnetar's incredibly powerful magnetic field would change the shape of the atomic orbitals from being relatively spherical and would distort them into the shape of a rod. If a magnetar were to get as close to the Earth as the Moon is, and we could ignore all the gravitational forces it would produce, the magnetic forces alone would be enough to wipe every hard drive on Earth. Another interesting thing about magnetars is because they have all this heat in these fluid dynamics, along with the magnetic field, they produce starquakes. And these are massive eruptions of gamma rays that flood the space around them and reverberate throughout the galaxy. And in fact, we've even detected gamma ray bursts that we believe have been caused by starquakes. Very good stuff. As I already mentioned, for this star to become a magnetar, the magnetic field has to be conserved through the rest of its life so it can be compressed down during the final supernova. And it is in the final stage of core fusion. As the helium and carbon atoms in this star fuse, they're producing heavier elements like carbon, nitrogen, fluorine, and neon. And since these elements are heavier, they tend to concentrate in the core. And this goes on until the carbon and helium are too diluted for fusion to continue. And when fusion runs out in the core of the star, there isn't enough radiation to keep blowing out the outer layers. And as a result, those outer layers collapse. But then the pressure gets high enough to reignite fusion in the shell of the star. And at that point, the star begins fusing helium in the shells where the helium hasn't been diluted yet. And since the pressure and the heat from the collapsing star gets so much higher, all those atoms start fusing at once. And this creates even more radiation that pushes the outer layers of the star even further out. In the case of this star, it's expected to push all the way out to a distance 300 times the radius of our sun. That's the equivalent of 1.4 astronomical units, which means the outer layers of this star, if it was our sun, would push out beyond the orbit of Earth, and it would stop a little before the orbit of Mars. And since the radiation coming off the star would be so spread out, the surface would look red, and this is the beginning of the star's red giant phase. The red giant phase of a star actually consists of several cycles of collapse, reignition, expansion, then collapse, reignition, and expansion. The helium in the shell will keep fusing for a few million years until it's all burned out too. And at that point, the star will begin to collapse again. Eventually, the pressure and temperature will get high enough for it to fuse carbon. And when that carbon starts fusing, it'll be hot enough to force all those layers out again. And that cycle of fusing carbon will last a few thousand years. And then it will move up to nitrogen and oxygen, and so on until it just can't produce enough pressure and heat to fuse any of these heavier elements. And each one of those phases is much, much shorter than the one before it, until finally the last cycle only lasts a few minutes or maybe a few hours. And with every cycle of collapse, reignition, and expansion, some of the star's material is completely ejected. And this is why we can see nebulae from dead stars that appear to have rings of material within them. And this is where the question of whether or not a magnetar will form from this star comes in. The magnetic field would have to be conserved through several cycles of collapse and reignition. And since a star's magnetic field results from plasma dynamics within the convection currents of the star, it's just not clear whether or not all these dynamics can remain the same all the way through a star's red giant phase. I did a quick search, and I couldn't find any studies where this phenomenon had been modeled or observed. And here's the second obstacle to this star becoming a magnetar. As I mentioned, with every cycle of collapse and reignition in the red giant phase, some of the star's material is ejected. And when that happens, the heavier companion star would certainly vacuum up a significant amount of that material. And since this star only weighs 2 solar masses right now, it's not clear that it's going to retain enough material through all this to be heavy enough for the collapsed portion to exceed the Chandrasekhar limit. There may only be enough remaining material for it to become a white dwarf. Nevertheless, this is the best candidate we've observed yet for being the progenitor to a magnetar. In any case, we know this star is eventually going to go supernova, and when it happens, the B-type companion star is going to be thrown clear, and it will go on to live out its life, with its blue giant phase and then a red giant phase of its own before it also collapses. And given its mass, there's a good chance it'll become a neutron star, though it's possible it'll only become a white dwarf itself. As I mentioned earlier, Wolf-Rayet stars produce these incredible nebulae from all the hydrogen being blown away. But in this star, we don't see any evidence of this having happened. If there had been a huge nebula blown away by this star, some of it would have been gobbled up by the B-type star. But since it would be coming out in 3 dimensions, and there would still be a shell of gas and dust around this binary system, we haven't observed any evidence of that. And that means this Quasi Wolf-Rayet star could not have started out as a star of 10 or more solar masses. It has to have a different origin story. What the researchers who wrote this paper believe is that the Quasi Wolf-Rayet star actually started out as a binary system of its own, and that these 2 older stars that were orbiting each other eventually both became a special type of star called a Type O subdwarf. These small stars consist mainly of carbon and helium, but they burn relatively slowly due to their small size. The researchers propose that the 2 stars lived out their hydrogen burning phases and then collided and merged during their helium burning phases. So basically, a merger of 2 stellar cores. That merger created one large star with a completely altered course, and its new course led it to come into a mutual orbit with its new companion. It's an amazing journey. It leaves so many questions to be answered, mysteries to be pondered, and one day they'll probably be solved. And with a little luck, we'll be around to see it. I hope you've enjoyed this journey of exploration as much as I have. I believe the ideal life is a non-stop process of learning and growing. Thanks for learning and growing with me. Now's a good time to leave your thoughts or information you'd like to share in the comments section below. And don't forget to hit the like and subscribe buttons on your way out. Stay on your game, and I'll see you next time on the Sexy Universe.